Welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I'm very pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a fantastic team at the University of California at Santa Cruz. Now, in this session, we have the privilege of shadowing members of the Splash team. We'll have several members with us in this session. That includes Douglas Filho, Lara Cullinane, and Raja GuhaThakurta, who happens to also be the Shadow the Scientist founder and distinguished professor of astronomy and astrophysics at the University of California at Santa Cruz. Now, the team this evening will be using the Keck II 10-meter telescope and the DEIMOS spectrograph here, as you can see, located near the summit of Maunakea on the Big Island of Hawai'i to study the kinematics and the chemical composition of the resolved stellar population in the southern disk of M31, which is the Andromeda galaxy, and its elliptical companion M32. Now let's go over to Raja to get us started. Raja, welcome.
Welcome. Hi, everyone. You are catching us on a night where the Hawaiian skies are clear, the conditions are good. We started this work a few hours ago. We calibrated the instrument before sunset, but the sunset around, or our nighttime observation started about half an hour after sunset, but that was about an hour and a half ago. It's 11:05 in California. It started around 9:45 or so is when we started. So nearly an hour and a half ago. I'm going to talk us through what we're seeing on our screen. I'm going to share my screen right now. But we're going to be looking at the DEIMOS controls. You know, there's one screen here. This is a second screen, a third, and a fourth. I'll describe what these are in the course of the next hour or two. But I'm going to take a quick pause because the first of our exposures just finished. It's reading out. You'll see that it says reading out right there, if you can see my cursor. It's 20% read out, but it's reading out all the way to 100%. And when that's done, it'll display the first 20-minute exposure. You'll see the integration time is 1200 seconds. It's finished a 20-minute exposure, reading that out, and it'll display it after the readout is finished. So I'm going to go to the display window so that we can see the read out 20-minute exposure, and Doug and I will look through that. But in the meantime, after we look through that, we will do a more thorough introduction. Okay, so you could hear readout complete. I don't know if you could hear that, actually. I'm going to stop my share and I'm going to reshare with audio so you can hear all the telescope sounds that are relevant. Okay, here we go. Doug, let's take a quick look. Oh, wow. Look at that, Doug. We're seeing continuum in every slit, pretty much. Let's see. I don't know if Doug hasn't rejoined yet. All right. Let's see. I'm going to wait for once Doug joins, he can introduce himself. Carlos and Julie, if you have a moment, please go ahead and introduce yourselves to the group here. If you have a moment, I'm going to unmute you. Give me a second to do that, please. Oh. How do I do? Carlos, you should be able to unmute yourself, and Julie, same for you.
Yeah. Julie, you want to start or shall I start?
You go ahead, Carlos.
Okay. Yeah, so I'm Carlos Alvarez. I'm right now at home, actually, in Waikoloa Village, not on the mountain, on Maunakea. And my job here is to support Raja's observations and the instrument scientist for the DEIMOS instrument. So essentially, I'm here just making sure that everything works on the instrument side. And if there are any technical issues, any problems, anything that prevents us and Raja from taking science data, well, I'll help and try to get those issues fixed.
Thank you, Carlos. Things are, by the way, our last mask alignment was super smooth. 2 iterations, it was done. After the second, so course alignment went well. First iteration, the masks were not centered. After the second iteration, all 3 were no, no, no. There was no rotation, no translation. It was very quick. And the seeing is about an arc second now, so it's good. Sorry, Julie, all yours. Julie, you're muted. Let me see if I can. Are you able to unmute, Julie?
I can now. Yeah.
Oh,
I
okay.
had
Sorry.
unmuted to tell Carlos he could go first, and then I guess that was my one and only chance. So sorry.
No, go
Hi,
ahead,
I'm
please.
Julie Renokim. I'm what we call a telescope observing assistant at Keck Observatory, which is basically a telescope operator. I'm up here on the top of Maunakea, which is why I'm in wool and long sleeves. It's pretty cold. And I basically run the telescope and point the telescopes where Raja or whoever my observers are want to go look at and help to make sure they get their data. I'm kind of the first line of defense if something goes wrong, especially if Carlos has gone to bed, I have to stay up all night no matter what. And so as other people go to bed, try to get their sleep. If something goes wrong, I'll figure out who to call if I can't fix things myself. And that's kind of what my job is. So
Thank you, Julie. Julie, you have the hardest job of us all because you're physically on a mountaintop in the cold, oxygen deprived, all of that. So
we do have some oxygen things that I could put on if I needed.
thank you. Thank you for this. It's really great. I'm going to, I see several names I recognize in the in the participant list. We have several UCSC students who have connected today who are part of our research group, and a few other students, not at UCSC, but who are also part of our research group. Stephen and Rohit, I'm thinking of the two of you. Rohit is on the East Coast. Stephen is at UC Merced, but he's working with us. Yael is at UC Berkeley. She used to work with us. She's as a high school student. And but now she's a college student at UC Berkeley. Who else do I see? I'm just scanning the list. Am I missing anyone? Thought I saw Esther on here. Just let me see if I can find her again. Yep, Esther, welcome. Esther, did you want to take a moment to introduce yourself? I'm gonna ask you to unmute if you want to take a moment to say who you are, and that would be amazing.
Yeah, sure. Hi guys, my name's Esther and I'm an undergrad student here at UC Santa Cruz. I'm new to the team, but I plan on joining and being a part of it next quarter. Yeah, I'm an astrophysics major.
And Esther, you're starting work on looking at variability of weak CN stars. That's going to be your research. That's a little removed from what we're doing on the telescope tonight, but welcome to the team. Thank you, Esther. And Stephen, I know you're at UC Merced, and welcome, Stephen. Welcome back. And let's see. Let me see if I can get you to unmute. Yeah, there you go. You should be able to unmute. What I'm going to do is see if I can. I'm going to give everyone the ability to unmute themselves, actually. So, but please use that responsibly. Stephen, go ahead, please.
Oh, yes. Hi, I'm Stephen. I'm from UC Merced. I worked with Raja and Phil Hins at UC Merced or UC Santa Cruz over the summer. I looked at star clusters in Andromeda, and I used data from Keck II, adaptive optics, and I compared the 6 star clusters to Hubble.
Thanks, Stephen. Thank you. Let's see, who else? I'm just looking at the list of participants. Who do I see next from our research group? Yash, if you want to say a quick word.
Hi, my name is Yash. I'm an undergraduate student at UCSC. I'm also an astrophysics major, and I'm just getting started on research with Raja.
And you'll be working with Avi. Yash, did you and Avi manage to chat a little bit today about?
Yeah, we spoke a bit, and like he pointed me towards the data. I just made
Excellent.
like one graph, but I just need to like talk to you about it once before I continue.
Of course. Okay. Thank you. Thank you for connecting. I know it's very late. Who do I see next from our group? Yael, you're next. Hey,
Hi.
Yael.
Hi, can you hear me?
Yeah, we can hear you. Where are you?
I am in my living room in my dorm because my roommate is asleep, so I can't be in there.
Of course.
But yeah, I'm currently sitting here doing my physics homework. Yay, freshman. So I'm majoring in astrophysics and cognitive science here at UC Berkeley. I worked with Raja for a couple of years back in high school. I think I started the summer after my sophomore year. I worked in his oral library group, so this is a little bit different from that, but it was still super fun. And yeah, now at Berkeley, I'm working with Professor Yuri Kolomensky, if you know him. But we are doing high energy like particle physics. So I'm helping to build a cryostat, which is super, super cool, getting a lot of really interesting things done.
That's fantastic. Welcome back, Yael. Let's see. Who do I see next? I see Rohit and then Annalise in that order. Rohit, go ahead, please. Super late for you.
Yeah, so hello, I'm Rohit, and I'm a final year undergrad student at Junior Tech College, Pennsylvania. And I have been working with Raja from a little over 2 years, I believe now. And I work on primarily right now on unusual stars in our nearby galaxies like Triangulum, Andromeda, like M31, M32, and M33. And it's been really good. We made good progress, and it's always super exciting.
Thanks, Rohit. And last but not the least, Annalise, if you have a moment to introduce yourself.
Good morning, everyone. I'm Annalise, a USTA from South Africa. I'm studying for UNISA PhD student and mostly focusing on DEIMOS stars and their light curves and anomalies in that regard. Thank you so much for this program. I appreciate it.
Thanks, Annalisa, and welcome back. All right, I'm going to go back to sharing my screen and walking through some of the things we are looking at right now. I'm going to make sure Doug is able to reconnect. Just a moment. I want to make sure that he doesn't have any difficulty rejoining our call. I'm just going to take a quick minute to let him know where we are with the observations. So please bear with me. So we are on a mask whose name is right there, M31 SRAA. I'll explain what that means in a second. All right. So we are studying the Andromeda galaxy tonight, as you've heard. In fact, I'll show you a quick display where you can see some of the individual stars in the Andromeda galaxy, each one of these dots. This is a very bright star. This is in the foreground. It's in the Milky Way, but most of these fainter stars you see here are in Andromeda. And we are working with something called a mask, M-A-S-K.
Sorry, so apologies. Are we supposed to be seeing something on the screen other than yourself?
I'm sharing my screen, or maybe my share didn't go through. Let me redo that. Are you seeing my screen now?
Ah, yes, it says program information.
Yeah, perfect. Thank you.
Mode, it just disappeared now.
Thank you for catching me on that, because I tried to share my screen, but it didn't go through the first time. But you should be seeing it now. Yeah, these stars that if you can see my cursor, these stars that you're seeing, and this very bright star in the right. The bright star on the right is in the Milky Way, but the other stars are in Andromeda, and we are getting spectra of some of these faint stars, not the ones you see in the picture, because the ones we're getting spectra of, their light goes through a slit in a metal plate. We don't see their, what we're seeing is reflected light of stars that we aren't getting spectra of. But these stars that we aren't getting spectra of are useful for alignment, for making sure that the telescope is pointed just right and rotated, the instrument is rotated just right. So here are, so the metal plate we're using, the name M31SRA, the M31 is, of course, Andromeda's name. So 31st object in the Messier catalog. We're studying the southern half of Andromeda, southern half of its disk. That's why the S, the capital R, we have a red setting and a blue setting. We're using a red setting for this particular mask because we're observing stars that are relatively low temperature and have most of their flux coming out at long wavelength. We also have we have another mask that we'll observe later tonight. The conditions remain good. That's called M31SBA, B as in blue. And that one will target the same patch of sky, same region of the sky. That's what the lowercase a refers to, a certain patch of the sky in the southern part of Andromeda's disk. But it'll be a blue setting, so it'll collect shorter wavelength light, actually a wider range of wavelengths extending to shorter wavelengths. And because of that, because we know we're targeting shorter wavelengths, we'll target a different set of stars that have a wider range of colors, wider range of spectral energy distributions. In particular, hotter stars in Andromeda will be targeted on that mask, whereas cooler stars are being targeted on this one, hot and cool referring to their surface temperatures. I did want to show you some of what we're doing right now is collecting 3 exposures. If you look at this little screen in the lower right, you'll see 1 of 3 has finished. 2 of 3 is nearly finished. It says exposing. I say it's nearly finished from this other window here. It's 973 seconds into a 1200 second exposure. So it's a little over 16 minutes into a 20-minute exposure. So as this counts up, 985, 986, 987, as it counts up to 1200, when it finishes counting up to there, in fact, it will then start reading out. And I'm going to stop and restart my screen share because I want to make sure I'm sharing audio with you. Yes, I am. Okay, good. I'm sharing audio. So you should hear the audio prompts from the system that tell us exposure or readout or exposure complete, readout complete. You should hear that very soon. This is useful for us during the night. We're taking a series of these exposures. 20 minutes is a long time. We typically will go off and do something else, read a paper, check our email. And so we don't want to lose valuable telescope time. So if it's an automated sequence, that's great. When one ends, the next one will start, as it is doing right now. You'll see I started a sequence of this very cryptic command over here that I've just highlighted, the GuhaI3. The GuhaI3 means go, integrate 3 times, take 3 sets of exposures. So it takes 3 20-minute exposures. So for that 1 hour, we don't have to intervene as astronomers or telescope operators. We don't have to intervene if all goes well. It'll do its own thing for those 3 20-minute exposures. But when that sequence ends, we have to intervene. We move the telescope to the next patch of sky, move in a new metal plate, and we'll see all that happen. But we are waiting for this exposure to finish. This is at 1085, so we are, what is it, about 2 minutes away from just finishing, a little less than 2 minutes away. $1100 at the 1140 mark. We'll be a minute away. We are 1.5 minutes from this finishing, but we'll go to a different screen. This particular screen, I'm going to zoom in a little bit. Can everyone see the screen okay?
Yeah.
Thank you. I'll describe what this is, but you'll see these, what looks like a barcode symbol, these nearly horizontal lines, and these vertical streaks, these very strong vertical streaks, like this is the continuum of a star. But you also see these diagonal streaks, like this very long streak here. If you pay attention to that, that will disappear in the next exposure. This was a cosmic ray hit in the previous 20-minute exposure. This 20-minute exposure that's about to read out, it's nearly done with the exposure, 40 seconds to go, 37 seconds to go. When it's done with this exposure, when it's done with the readout, I'll switch to that screen and you'll see that most things won't change. The second 20-minute exposure on the same set of stars, but cosmic rays will disappear or will appear in new places. And this anti-coincidence is exactly why we take a series of exposures. We don't take one long exposure, we take a series of exposures. All right, so the exposure is about to finish, so I'll keep quiet.
Exposure complete.
Could you all hear the audio from the system? Exposure complete?
Yes.
Oh, excellent. Okay. So now you see its status has gone from collecting light to flushing out the silicon device, flushing the information that it collected for the last 20 minutes is what's going on. Flushing, but not just flushing down the toilet, flushing to hard disk. So we are saving this exposure right now. It's reading it out. When this gets a little closer to 100%, I'll switch screens. Maybe I'll do that now. And if you pay close attention to some of these long cosmic rays, you should see this one disappear, and you'll see different cosmic rays appear, but otherwise, the general pattern shouldn't change because it's the same mask, same
CCD
slits.
readout complete.
There we go. Readout is complete. There you go. You saw the cosmic rays disappeared, but the rest of it stayed the same. So this is the new exposure. Looks very much like the old exposure. And I can spend a little bit of time talking about what the horizontal lines are. The horizontal lines are actually the glow of the Earth's atmosphere. Oxygen in the upper atmosphere, mostly oxygen, but other things like ozone and OH, these glow, these substances glow. The night sky isn't completely dark. They glow at very specific wavelengths. And each wavelength at which it glows produces a near horizontal line here. Slightly tilted by design. That's how the mask was designed. It's not perfectly horizontal, these lines, but the vertical streak is the spectrum of a star that the slit was designed for. So you can see that this particular slit, that if you can see my cursor, I'm going to zoom in. Let me see if I can zoom in. I'm panning right now, I'm not zooming. But I'm going to, now that I have a bright star centered here, I'm going to zoom in some more. And you'll notice now that every one of these vertical bands is a slit. It's actually the spectrum of a slit. I shouldn't say the band is a slit. Each band, each vertical band, separated by these dark lines, dark vertical lines, is a cut in a metal plate designed for a particular star, typically for one star, but sometimes multiple stars shine through, and we get a spectrum of the star that it was designed for. Some of the stars we target are faint, some are bright. So you can see that this star that's in the center of the frame was quite bright relative to, say, the neighbor on the left, and especially the neighbor on the right. This star, if you can see my cursor running up and down, this one, the star is barely visible, the one that it was targeted for. And that's, again, we know this because Andromeda has stars of different brightnesses. We're targeting a range of stars of different brightnesses. I'm going to pan to a different part of this image. Here are two very bright stars.
Sorry, my apologies. Can I just clarify?
Yeah, please.
I mean, I didn't, forgive me for being slightly late. I didn't have a chance to introduce myself, but I'm Andrew. I'm an amateur astronomer from the UK. So unlike most of the participants here today, I don't really have that much expertise. So I do apologize for asking basic questions and hope it doesn't bore you.
Not at all. That's what these sessions are for, Andrew.
So am I right in understanding that the star spectrum is the vertical light line that goes down the middle of one of these bands?
Exactly. It is. It doesn't go exactly down the middle.
Horizontal lines crossing that vertical line, as you say, are just the spectra of stuff in the Earth's atmosphere.
That's correct. That's correct. So what happens is, it's interesting. One is extended one way, one is extended the other way, and I'll explain why. The star, so what is running vertically is wavelength. What is changing as you march along vertically is wavelength. So blue light lands, and you know what? The main screen here is a zoom in of what you're seeing on the left. Okay, so on the left is the overall single data frame, single 20-minute data frame. And what we've zoomed in on, if I show you what's at the bottom of this versus at the top of this, we can zoom into different sections of this image. You can see it's particularly dark in this corner, dark in the lower. In all the corners, it's dark because of a phenomenon called vignetting. Not much light is reaching the system there from the 10-meter telescope. But yes, the vertical lines, each vertical line is a spectrum of a star. It's not perfectly centered in the band. You'll notice in some instances, it's quite a bit closer to one edge than another. A good example might be, let me see. Let me find, oh yeah. If you can see my cursor, this bright star is quite a bit closer to the left edge than to the right edge. And that's okay, that's part of the design. You can see this from, if you look closely, most stars are not perfectly centered, and that's deliberate. It has to, it's not deliberate because it's gaining us anything scientific, but it's helping us calibrate things better. That miscentering is actually helping us calibrate. I won't get into the details of that right here. And you'll notice that some of the slits, these bands are slits. Some of the slits, like this one in particular, is quite wide in the X direction. That means it's a long cut in the rectangle. So it's a long rectangle that's been cut into the metal plate. And this one happens to intercept multiple stars. The one that was targeted, which is the one my cursor is running along, but fainter stars to the left and even a faint star to the right. And these are serendipitously detected stars. You can see serendipitous detections in this slit, the sort of the third complete slit from the left. You see one targeted star, but you see other stars that are in the slit. The next slit over, the one where the fourth complete slit from the left, also has multiple vertical streaks, multiple stars within the slit. Let me see. Let me zoom out a little bit. Some of these are completely burnt out. This one that my cursor is on. This particular slit is not a science slit. It's something that was has something called an alignment star used to line up this mask precisely. That's the role of that cut in the piece of metal, is to use the star in that slit for alignment purposes only, not for science. You see a couple of those alignment stars in the far right here. In fact, even in the zoomed out version of the image, you can see 3 of these very bright bands, 2 in the middle, 3 in the right. Again, these are alignment stars, I believe. These are all alignment stars. Not this one. This is not an alignment star, nor this. So not the 2 in the middle, but these 3 vertical streaks on the far right, these are all alignment stars. 1, 2, 3 on the left, and 3 on the right, and these 3 on the left. 1, 2, and 3. Some of these alignment stars are very bright. They're actually in the Milky Way, but they do a fine job of serving as lampposts, so we can line things up perfectly. Precisely, I shouldn't say perfectly. And no physical experiment is ever, perfect. And you can see that in the upper part, which is where I'm clicking, the upper parts, the Earth's atmosphere is super active. It puts out lots of emission lines in the red part of the spectrum, very few in the blue. See, the blue is much more quiet. In the lower part of the spectrum, the blue wavelengths. And just to give you a sense, we're going from about 600 or 650 nanometers at the bottom to about 900, 950 nanometers at the top. So we're covering a swath that's about, for every slit, it's about 270 nanometers or 2700 angstroms. Again, the upper part is very, very active. The air glow is very active in the red part of the spectrum. You'll notice that the upper left rectangle here is dark. One of our silicon devices failed or has been failing. It's been on and off. So this this instrument is going to undergo an electronics upgrade early next year. So, all right, let me pause here. Let me pause my explanation, and I'm going to check in on Doug to make sure he's able to connect.
I'm already here.
Oh, Doug, you're here. Okay, sorry. Doug, the data look very good. The second exposure looks terrific, actually. And we're a little over, or we're close to halfway through the third. Yeah, I was just, Doug, did you want to introduce yourself? I'll stop my screen share.
I'm Douglas. I'm a 4th year graduate student at Santa Cruz, and been working with Raja on this southern disk, which is where we're looking at now, southern disk of Andromeda, for a little over a year now. So this new data is important for us getting enough science targets on the disk to get a sense of how these stars are moving. That's why we're taking their spectra, really, is because it's a lot more time intensive to take the spectra of a star than it is to just measure how bright it is. But the benefits are that you get to know how fast the star is moving, either towards you or away from you. And if you get enough of those, then you get a good sense of how the whole disk is moving, which is what my research is about. So, yeah.
And Doug, you have an important day on Monday. Do you want to describe that process?
Yeah, it's just the qualifying exam is just a process that all PhD students have to go through, where I basically have to give a 1-hour talk outlining my thesis. So I've been working on that on and off throughout tonight, which is why I've been sort of MIA for a lot of this.
Thank you, Doug. Thanks. That's great. I see Sarthak has joined since I last scanned. Sarthak, if you want to quickly introduce yourself. I've been asking those who are working with our research group or have worked with our research group to quickly introduce themselves. So Sarthak, take a moment to please introduce yourself. Thanks, Doug.
Oh, hey everyone. I'm Sarthak from India. I'm a first year undergraduate student at Ashoka University. I'm majoring in physics and minoring in CS. I was a part of the science internship program in 2022, where I worked with Professor Raja on TDEC survey. It was a very amazing experience for me. And yeah, we'll be working, we are finding someone to work with to do some further research on the same topic. So yeah.
Thanks, Sarthak.
Yeah.
Let's see. Let's see. How are we doing on this exposure? We have another 5 minutes to go. More than 5 minutes. 700 done. 500 seconds to go. 450 seconds to go. All right. Did anyone have any questions about what you were seeing on this? Again, let me see. I've forgotten your name. Was that Andrew? You were asking questions about?
Oh, sorry, forgive me. So just turn my video back on. Yeah, hi. Oh,
Andrew, yeah.
Yeah. So can you show the screen back again?
Of course, absolutely. We'll do that.
I'll go back to some of my really basic questions.
No, this is great. This is great.
Do apologize to the group for those. So on that screen, if you don't mind me asking, there's like a horizontal band in the middle that goes across. That's a light band. And I noticed there's also one looking at the left-hand side, which is a dark band right in the middle as well, that goes right across the whole screen. What are those? Those horizontal bands?
Let me see if I can find the horizontal band.
You've got one. There you are. There's a dark one there.
Yeah. So that's a gap between. So there's a total of 8 detectors, 2K by 4K CCDs that are in the focal plane of the camera. 8 of them. 1, 2, 3, 4 across the bottom. If you can see my cursor, 1, 2, 3, 4. Again, 2K in this direction, 4K in that direction. So these are CCDs 1, 2, 3, and 4. CCD 5 is the one that's faltering. 5, 6, 7, 8 are across the top. So when you get a spectrum of a star, it goes across 2 of the CCDs, and it covers a total of 8,192 pixels, because these are 2048 by 4096 pixel CCDs. So the spectrum of each star, in fact, you can see this in the zoomed in view. The spectrum of each star has a little gap in it because, physically, there's a gap between these 2 pieces of silicon. So a small chunk of the spectrum falls on the floor, doesn't get collected. That's the horizontal dark band. I actually don't see a horizontal bright band. This banner at the bottom is part of the display window, but it isn't part of the...
I think you might mean the horizontal cut that you did to get that graph.
I had done a cut. I had done a cut just to get a intensity profile. That was done in software. Yeah.
Forgive me. So one other silly question, if you don't mind.
These are not, by the way, these are not silly questions. These are great questions. So please
well, yeah, it might seem silly. As I say, I'm an amateur. I'm a family doctor is my profession, but that doesn't mean I know much about physics. But I'm a very passionate amateur astronomer. But so if you do astrophotography and astronomy, I mean, we're talking about using CCDs now that might be giving anything up to sort of 64 megapixels in amateur astronomy. So it seems very surprising that on a telescope as expensive as the one that you're using a CCD that seems to have so few pixels. And in fact, they're not even one CCD; it's 8 CCDs rather than one single one with gaps in it. Forgive me for asking that, but
No,
why
that's a great question. That's a great question. So first of all, this instrument is going to undergo a CCD upgrade next year. These CCDs go back to 2002 when the instrument was first commissioned. So it's a 20-year-old, well, 22-year-old instrument, spectrograph, CCDs. They're more than 22 years old because that's when it actually saw first light on the telescope. The construction happened over a 10-year period before that. So these CCDs are actually quite old. And back then, it was quite the deal to get 2K by 4K and to get 8 of them aligned in this format. So each CCD is an 8 megapixel device, but there's a total of 8 of them. So overall, it's a 64 megapixel device.
Right. Oh, I see. Okay. Yeah, I'm not calculating properly in my head, am I? That's quite right. You say it's actually a lot more than it sounds at first sight.
Yeah. So overall, it's a 64 megapixel device. Each of the 8 is an 8 megapixel device. But yeah, this is small by today's standards. And the other thing that Doug was saying, which is spectroscopy generally uses fewer pixels than imaging. Imaging, you're using, you're trying to really tile the focal plane with silicon. So the biggest camera that astronomers have ever built is one that's going to go on the Rubin telescope. And I forget how many pixels that is. Doug, do you remember off the top of your head how big the Rubin camera is going to be?
No, I do not.
I'll look it up. I'm going to do a quick.
Just so you know, also, Raja, in about 2 minutes, the last exposure will be
okay.
done.
So I'm going to go back to screen share. Sorry. Let's come back to that question after we finish this exposure. Yeah. So this is going to read out in 2, and we're going to go to the next mask.
I already highlighted the next.
You did. Okay. Are we going to do BA next?
BA, yeah.
Okay. So I will, as soon as the readout starts, which will be in less than 2 minutes, I'll go to BA and I'll change the. Yeah, so we have a mission critical moment coming up where we switch masks. So that's why we're just sort of, I'm going to put our discussion or explanation on pause until we can get that. There you go. Rohit says it's a 3.2 billion pixels, gigapixels. That's crazy. That's it's not crazy. It's real. It's been built. The camera is ready, and it goes into operation about a year from now. Yeah, 3200, Rob. That's right, 3200 megapixel, or as Rohit wrote, 3.2 gigapixels, 3.2 billion pixels. Yeah, this is a small array by comparison, 64 megapixel.
Okay, about 10 seconds, I think.
All right. So Doug, same drill. You communicate with Julie, and I'll
I mean, I think yeah.
Okay. BA. So Carlos, there's going to be a grating change.
Okay, I think we're good to salute to the next target, Julie, if you can hear us.
So Carlos, I have a question for you. We're going to switch to the 600 ZD grating.
Yep.
Will it automatically go to like the 7200 wavelength and then I should set it to 0?
Yeah, it will. Yeah.
Okay.
It knows what was the last wavelength that was used.
Okay.
So
I'm going to switch blocking filters as well.
You can do that in parallel.
And I'm not going to change. Doug, I'm not changing the exposure time for now. Let's just let's just see where things are. We can always adjust. All right. So I'm just going to watch for the grating while Julie's moving the telescope.
readout complete.
So Julie's actually moving the telescope, or will be moving the telescope soon. You'll see things change over here. As we move the telescope, the stars won't be dots on this image. There'll be streaks as we move the telescope.
Actually, Roger, the telescope will not move because the position is the same.
Oh, you're right. This should be a very quick alignment then. This will be a very, very quick alignment. In fact, it's the same alignment stars, right?
Yeah.
So we can go straight to find.
Yep. So you guys didn't tell me that before, so I did slew and rotate. But let me see, I can put it back to the rotator angle that we had.
Yeah, if you could go back to base. Oh, sorry.
So is it the exact same? It's the exact same alignment
Yes.
as the previous mask? Okay.
Yeah. So you had marked base on that one, right, Julie? So we could just go back to that. Sorry, we should have told you.
No, because I slewed. So, but I recorded parameters so I can get back too close.
Perfect.
We'll still have to find a line.
Sorry about that.
No, that's and Julie, it's both rotation and translation that gets matched. Oh, perfect. Okay. All right.
Yeah, you don't need to do the course alignment. You can go directly to the final alignment.
Okay, perfect. Doug, do you want to do that?
Go ahead.
I'll do it.
Once we are guiding though, just bye for Julie. Are we there already, Julie?
No, hang on.
Just let us know when things are ready for.
Star, where
Okay.
it was before.
Sounds good.
I think maybe you can go.
Okay, now
Should I
it should be
start?
good for the final alignment.
Okay, go ahead and
Okay,
start final
perfect. I'm going to
alignment.
start.
Yeah, he's complaining about the mask name. So you should say.
Oh yeah, that's fine. That's easy. That's the extra A, right?
Yeah, that was what was complaining about. Yeah, Raja, maybe you can declutter a little bit the FCS plot just to see, because it did a big swing as we were.
Sorry, Carlos, could you repeat that? I couldn't quite
Yeah, the FCS cross correlation plot may just make it a little bit bigger.
Okay, of course.
Complete.
Just to see how far it went, because. Oh, okay. It didn't go
That's
that
not
far
bad.
away.
That's not bad. It's close. I'm going to bring it to 1.
Yeah.
2.
Yeah. 2 probably is good.
2 is good, huh?
Yeah.
Not
There we
bad.
go.
Okay.
So yeah, as soon as
CCD readout complete.
So we should go to final line. Okay, this looks very good. I'm going to do send moves and retake.
yeah. So a little bit off in X, but
A
looks
little bit,
okay.
yeah. But the
In
image
Y,
quality looks
yeah,
good.
looks good. Yeah.
So what it's doing right now is it's taking a series of short exposures, 20-second exposures, in something called zeroth order to get images rather than spectra.
Exposure complete.
And it's using that to fine-tune the alignment of the mask. So the translation, XY translation, as well as the rotation. You see X instrument, Y instrument, and rotation. Those are the three parameters that it's
CCD
fine-tuning.
readout complete.
Beautiful.
You are
All
aligned.
set. All set. Okay, I'm going to go and go back to.
Hey, Yuri, can you mark this here, please?
Okay, and I have to mark this as
Base is marked.
7200, right?
Yeah, that's correct, Rasha.
Okay, thank
Good
you.
to go.
Thanks, Yuri.
Thanks, Julie. So this is a blue mask, SPA. And Doug, I propose we start with 1200 seconds and then we can adjust
Yep.
from there.
That sounds good to me.
Doing 3, I'm starting a set of 3. I'm starting it because I think everything is lined up. SPA, please take a look. Correct rating, correct filter. Yeah, okay. I've started it. Let's watch let's watch this thing line up. Let's watch the FCS catch up.
Yeah.
So FCS is something called a flexure compensation system, which is a really fancy system within the spectrograph that compensates for the fact that it warps under its own weight it's a cylindrical shaped instrument. As the cylinder rotates, as it rotates about the axis of the cylinder, the instrument flexes under its own weight. And because we want to maintain everything to very high precision, to a quarter of a pixel precision, it makes these wonderful adjustments to compensate for flexure. FCS, that's what this big window here, FCS control, flexure compensation system control. Flexure is bending, of course, under its own weight. So it looks like that was a false dawn, Carlos. It looked like it was,
Yeah.
yeah.
It
So,
overshoot.
yeah, I'm gonna, yeah, oh, it's much closer now. Just as I spoke, I
mean,
embarrassed it into correcting.
That
Yeah, there we go.
that correction that we saw before, it was also after slight slew in rotation. So
Right,
maybe.
right. This looks good. It's getting close.
Yeah,
This
it's
green box, when the
right.
green box enters this, when the green dot enters this pink box, where it's gotten close, it's overshot. But once it enters that, then things are lined up to within tolerance and it'll start the exposure. So it's getting there. It's not yet there. It's getting there. I'm going to zoom in some more. As soon as that green box moves in, you'll notice that the status says idle, and now it says erasing. It's erasing the CCD now that things are tracking in FCS. Now it's about to start the exposure.
Very nice.
These alignments are going fast.
Very
That's
quickly,
good.
very quickly. Yeah.
Yeah. So let's adjust our spreadsheet times, Doug. Let's look at that next.
Sure.
Let's see where we were here. So
Right
this one
now
just
it's about
started.
9 p.m.
So we shaved off 5 minutes then. Right?
Yeah.
I'm going to adjust this to 2100 and for the previous one and start this one at 2100. And that would normally go to 2220.
Yeah.
If we were doing the full complement. Let's look at how good or bad the seeing is and make a decision accordingly. Okay. So I'm going to go here. I don't think the seeing has changed dramatically. I mean,
Rasha, I'm gonna take control for a little bit of the control 0 VMC because I see that the FCS status is toggling between tracking and warning. And I think that warning is because of that, what we talked about before, the gradient tilt offset, I think, is more than 100 angstroms.
Got it. You
But I
take
wanna
over,
make
please,
sure-
Carlos. Yeah, you please
Yeah.
take over. I'll come back to the, I see what you mean about the warning. I can see it going from green to yellow.
Yeah, I
please-
want to make sure that it's not something to be concerned about, essentially.
Right. So folks, Carlos is going to look into a possible instrument situation. I mean, the exposure is going on. It's not stopped. You can see. It's collecting light. It's about 2 minutes into the 20-minute exposure, but we want to make sure the instrument is functioning properly. Carlos, every time it goes into warning mode, does it pause the exposure?
No, it's just that oh, you mean like the science portion?
Yeah, it doesn't,
No,
right?
no, it doesn't. It doesn't.
Okay. That's good to know.
Just it's just when it does the flexure compensation loop, every time that checks what the gradient tilt offset is, if it sees that is larger than 100 angstroms, I'll pop up that warning. But it keeps, as soon as it keeps doing its job, we are good. But I want to verify, because there are other reasons why you could have those warnings as well. So I just want to make sure that this is the reason why we are getting the warning. And if that is the reason, then we are okay.
I appreciate you looking into it. We'll come back to the seeing measurement later. No rush.
So we are in slider 4.
Do you think it's a slider 4 issue, or you think it's
yeah,
general?
well, it's a slide. I mean, it's not because it just happens to be like that. I mean, you remember it struggled a little bit when we were matching the FCS reference.
Yeah, I remember that.
During the afternoon calibration, it took a while to convert. But I'm looking at the value, and you see on that terminal that is on the control 0
Yeah,
BNC.
989.
So you see the where I am highlighting.
Yeah, I see that. Yeah.
So it's only one. So the warning is triggered when the gradient tilt offset is above 100 encoder counts.
Yeah, okay.
So I was saying angstroms, but it's actually encoder counts.
Okay.
And we get 127. So it's just a
little bit over.
So I think that's fine. I mean, we've observed even with this value being like 150 or close to 200, and it's okay.
What is one encoder? What is one encoder count in angstroms?
I don't know exactly, actually. In fact, I'm surprised that says encoder counts, because I thought they were angstroms, but
I see.
apparently they are not. So let me just check.
Okay, no problem.
Yeah, they are encoder counts. So. Yeah, I don't know how much that.
No worries.
In fact, it could be that would, rather than translate into angstrom, it's gonna translate into, because it's a tilt, isn't it? So it's gonna translate into an angle rather than a wavelength, which will translate into some angstroms as well. But okay, so I think we are gonna be okay with this. The only thing is that you hear that cuckoo sound.
Yeah, I hear that. That's the warning.
When there is a warning, and if that warning just is triggered at the right time, then yeah, you're gonna get that alarm to tell you, oh, you are taking science data, but the flexure compensation system is not tracking. So, but you can ignore it. It's just a little bit annoying that it's gonna be telling you from time to time.
No worries, no worries.
It's gonna be triggering from time to time that cuckoo sound. I mean, we can disable it, but I like to.
No, it's good.
To keep it on, just in case there is a real problem, you know. So you get those sounds sporadically every now and then, we are good. If we start getting them like persistently, then I'll take another look at it. But I think we are good. In summary. So what was the scene? Did you measure that?
Oh yeah, let me go measure the seeing.
Star 3 could be like,
I'm gonna look for these all look good. I'm just looking through all of them.
yeah, any of those could give you a good value.
Any-
Oh, okay. Then,
Yeah, I just wanted to look through all of them first. Yeah. Okay, let me go to this one. I guess P, right?
yeah,
And I wish it would remember the
yeah,
parameters from
would be
before.
nice.
Yeah, it would be nice.
Okay, that looks
Afford to go
very good.
bigger. I can afford to go 15, right? Does that look good to you, Carlos?
I think that looks pretty good to me.
Okay. Oh,
Oh,
the
that
seeing has
looks,
improved tremendously. 5.92.
yeah,
Okay, so what is that? That's better than 0.7. Let me see. I'm going to calculate this.
the air mass is much better than at the
Yeah,
beginning of the
I
night.
think we can
So
cut this exposure time then. 0.1185. It's exactly 0.7. Exactly 0.7. Doug, I'm thinking we can cut this a little bit.
Sure, yeah, in order to get the last one.
Should we just let's plan this out. Let's see if we did. So our first of all, alignment is not taking 20 minutes, or alignment plus readout is and FCS are taking less than 20 minutes, which is good news. This one started at 9 Hawaii. Is that right? We're 4 minutes into it. Let me double check.
Yeah, yeah.
Yeah, little over. Well, actually, let's see. It's 500 sec.
Yeah, it was basically at 9.
Yeah, we're 8 minutes into the exposure, right?
Yeah.
480 is 8 minutes. Yeah. Okay. So it's a little. So it's probably.
Well, Raja, even if you said that we're gonna hand it off at
08.
24:08.
Yeah.
Even if we just keep it like this,
Mm-hmm.
with the current times, if we assume an hour and 20 for this next one,
Mm-hmm.
that'll start at 22:20 and then go to 23:40. And then we'll have 23:40. So that's what? That gives us 30 minutes about. So we need
For
to
the last one.
get another 30
Another
minutes.
30 minutes
And if
roughly.
we say that instead of an hour and 20 minutes, it's going to take an hour and 10 minutes.
Yeah, let's do that.
So an hour and 10 minutes, that'll put us here. So that will.
I'm going to switch row 4 to R and 10. That's 22:06, I think.
So yeah, I think that we can. Then this last mask is going to be about 40 minutes or so. So if we can
Shave off a little
save-
bit. Yeah, 5 minutes.
Yeah.
Let's shave off 6. Let's make it 18 minutes.
Okay.
18-minute exposures.
Okay.
6 from each of 2, right?
Yeah.
So that'll be 12 minutes. Yeah, I think that'll be good.
Okay. Do you want to change that?
Yeah, I'm going to change this to 16, right?
Yeah.
And then the last one will be 16 to
the end.
Which is 0, 0.
Do we want to pad some time for the arcs and flats that we didn't take?
Oh, that can go into the other people's time because they'll be on a different instrument.
Okay.
So we won't need to budget for that.
yeah, you don't need to spend on sky time for that.
So when is the changeover? It's at
08.
08. No, 06, right?
Oh, 06 already.
I see
Hmm.
06.
Time
I'm looking,
flies.
am I looking at the correct page?
Yeah, you are looking at the correct one. I mean, it was 08 like 2 or 3 days ago, so
Yeah, it keeps changing.
it keeps changing. Yeah.
So it looks like at this rate, we'll only get 50 minutes on the last mask, including overheads.
Mhm.
Doug, what do you think? We can cut it a little more. We can cut it to 17 minutes instead of 18.
It's whatever you think, Raja. I think that 50 minutes with overheads will give us a little over 40 minutes of time. And
The
that's
last one, you mean?
yeah, that'll
Oh, yeah, because that's the start time. It doesn't include
yeah,
overheads.
that's the start time.
You're right.
So I think that's a
That's
good
fine. That's fine. You're
good.
right. That I had forgotten that that's the start time. So in 50 minutes, we'll probably get close to what, 45 minutes of exposure.
Yeah.
That's fine. Let's leave it as it is then. So we are then switching it to, we said 18 or 19?
Yeah, you said 18.
18. So what is 18? So that's taking off 2 minutes, 240.
It's
So that's
180. Yeah, 1080.
1040. Oh, isn't it?
It's 1080.
Oh, yeah, you're right. 1080. I can't do my math. Okay, I'm going to switch this. One of the cool things about this instrument is you can change the exposure time during an exposure.
Okay. Good stuff.
Good. I'm really happy with how this is going. The seeing has really
Improved, yeah.
tight seeing it helps everything, right? The alignment goes quickly and the exposures can be shortened.
All right, is it okay if I go work some more on my
Yeah, please do. Of course.
Okay.
Of course. Yeah. Let's see. So this one. Actually, this might be useful for people to see. This image you're looking at on this screen is what we are using for mask alignment. Let me try a different stretch, 6,000 maybe. Yeah, there we go. Maybe let me try 5,000. Zoom in. Okay, yeah, now if we zoom in, you can really see things. You guys can see that this is what you're looking at on this image is a square. It's actually a square cut in a piece of metal as opposed to these rectangular cuts. By the way, if you look at this rectangular cut, if you can see these two white dots, these are two stars shining through that slit. One of those stars was targeted, one of those is a serendipitous spectrum. But these 4x4, the dimensions of these squares, I'm going to give you an angular dimension in the sky. It's 4 arc seconds by 4 arc seconds, where an arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree. So what is 4 arc seconds? It's 1/900th of a degree. It's nearly 1,000th of a degree, a little over 1,000th of a degree. So it's a tiny patch of sky. By comparison, the full moon's diameter is half a degree. So we're looking at a tiny patch. This is 1,000th of a degree. So what you're seeing is a star shining through, and the software we were using earlier makes sure that the star is shining, that the telescope is aligned such that the star is right at the center of that box, of that 4x4 box, to within a very high precision, to fraction of an arc second. And when that's the case, then we can be sure that faint stars are shining through each of the rectangular cuts that you see elsewhere on the image. So this is what this is called an alignment image. It's used to align an image. Okay, let's go back to this. So we are nearly done with the first exposure. We are within less than a minute left.
Exposure complete. CCD readout complete.
So we're going to look at this exposure, one that finished reading out. Well, I'm going to direct my question mostly to the UCSC undergraduates who are on this call. Let me see who's on this call still. It's very late at night. Let me just see if I can. Yash, did you have any questions about what you're seeing here? We're throwing a lot at you. You haven't seen DEIMOS in action.
I mean, I do have a few questions, but like most of them have been asked. But if they do come up, I will like message in chat or unmute.
And you said you were able to make, was it a color plot that you were able to make with Avi?
Yeah, but I'm still not like sure. Like, do I use the Vega magnitude? And
yeah,
like yes, I did with that. But the data that Avi showed me includes like more than 100 files, and I'm not sure which file to use. And that's all for wild field camera. So I just took the first one for now, but just to like to see if I can do it properly.
Let me see. You said there were 100 files, and did
More
you
than
say
100?
More than 100 files? Okay.
Yeah.
I wonder if there should be a consolidated catalog, single file. It's a large file, of course. Do you remember the name of the file?
I mean, can I send you the link in chat or something?
Yeah, you
could
can.
see.
Yeah, you can just put stuff in the chat of the Zoom, of the Zoom chat.
I sent it to you on direct message because this is what Avi showed me. Zuo Chen, she didn't reply yet with the.
No problem. I'm going to be
data.
talking to her soon anyway, so I can ask.
Yeah, but
let's
using
see.
what Avi showed me, I made one graph.
Okay, let me look at this. These are WIFC3 only. Oh, let's see, what is it? Let me look at the full file name. Okay. These are you're saying there are 100 files on this. Okay, if I hover over any one of them, I'm looking at the full name at the bottom. And
yes, I used the first FITS file.
Okay,
and use the first text file to like index it and find the Vega magnitude of the color with filters.
So HLSP is the Hubble Legacy thing, something like that. What does HLSP stand for? Hubble Legacy Science Product, something like that. PAT is the name of the survey, of course. HST is Hubble Space Telescope. WIFC3, UVIS, ACS, WIFC, and WIFC3 IR. So those are all three cameras and modes. Okay, so that's what each of these is. Do you see it says B23 in there?
Yeah.
That's the 23rd brick. There are 23 bricks. If I hover over the very bottom one, I bet it'll be brick 1. I'm going to guess that.
Yeah.
Is it brick 1?
Yeah, it said brick 1 East, I think.
Where do you see that in the name?
It had shown like on the bottom left, but let me check on my laptop.
It might be the joint for all of it. It's 99.
I think it's the whole thing, yeah. Yeah, see, brick 01 is the third last entry. So you want the last entry, which is everything. It's concerned. You see, most of these entries have a brick number in them. B03, if I scroll down, B03 again. So there are multiple files for each brick. Right, Rohit? I think you're right. These are...
Yep, there are east and west for all.
Oh, half bricks. Okay. Those are half bricks. So let's see. Was the first one a half brick also? Oh yeah, brick 23 west. Brick 23 west. Brick 23 west. Looks like there's more than one file for each half brick. There's 3 files for each half brick. What is the difference?
One's a text, one's a FITS. I'm not sure what the other one is.
2 of them are text. One of them is a FITS. The first one's a FITS. The next one is a gzipped text file. Third one is a it just describes the columns. That's what it is.
Yeah.
Then, okay. So there are a total of 23 bricks. Each one is split up into a east and a west. But then I think Rohit is right. The very last data file is what you want to use because that's a consolidated one. It includes all bricks, east and west. That's the one you want.
But like, which text file do I use to like
You should
index
use the FITS file.
Okay.
Because I think that, right, Rohit?
Yep.
Yeah, you should use the very last file on this. It's a big file, it's huge. So you probably want to do something like, you know, I mentioned those cuts, right? Where you take out things that are F814 is brighter than 26. Keep just that.
Okay.
But you want to work with that. I mean, look, if you want to deal with smaller, more manageable file sizes, it's fine to use what you're using. But ultimately, we'll want to do this analysis on the full galaxy. On the
Okay,
FITS
makes
survey,
sense.
rather. Rohit, we have a meeting tomorrow, right? With Bob and Kim.
Yep.
Okay, excellent. Okay, let me go back to the screen and see what's going on here. So the first exposure is finished. It's reading the second one. Oh, we're not reading. It's in the second of the three, 2 of 3. But I'm impressed by data quality of the first one. Stephen, any questions from you? Yael, Sarthak, Rohit, any of our research students, if you have any questions about what you're seeing here. I think, yeah, sorry, go ahead. Any questions at
There
all?
was one where we had 2 stars. Can you look at that?
Sorry, say that again, Rohit.
There was one where there was like 2 stars in same slit, so.
Oh, yeah, there are many such. That was in the alignment image, but you're saying even here, look at the number of stars in some of these slits, many. You know, the bright stars, especially the young stars, as you know from your Wolf-Rayet work, some of them are in very crowded regions. Look at the brightness of this star, super bright. But, you know, this is individual. This is an individual, what is it, 18-minute exposure? I think, right, 18 minutes. We're lucky, the conditions are really good.
How do you like decide if you should take a longer or shorter exposure? Do you just kind of vibe it?
It's a good question, Yael. Yes. Yes. We are, so first of all, not all the stars that we target on a mask are the same brightness. So even if you take a very short exposure and or the conditions are really poor, you're going to come away with a few spectra because the really bright stars that are on the mask, you'll get decent spectra for those anyway. And the reverse is true at the opposite end. If you have really faint, there are faint enough spectra that even if the conditions are really good and you're taking long exposures like hour-long exposure, it may be marginal whether you can measure a velocity or not. So that's sort of the situation with the mask. But what we're trying to do is, you know, partly it's logistics. This is the last half night we have on the telescope for the foreseeable future. We don't have any other time this observing season. Andromeda is not up during the spring, so we would have to put in another proposal in the spring to get time in the fall. We probably will put in other proposals, not Andromeda proposals. So from a standpoint of Doug's PhD thesis, we want to see, we want to leave things, nicely wrapped up. It's better to get good data on fewer masks and fewer stars than to leave ourselves with partial data, because the partial data, topping that up is not going to happen anytime soon. So it would be wasted if we had sort of partial data on some masks. So those are the sorts of considerations, and we were trying to squeeze things in to get them to finish by, whatever, 12:06, which is the handover time between our half of the night and the next half of the night. So I'm not answering your question, but partly it is experience. We've taken data in various seeing conditions. 0.7 is good seeing, and I know that given the brightnesses of our stars, we have 0.7 arcsecond seeing. We should, 1 hour, a 1 hour exposure is little overkill. So we shortened it to 18 times 3, 54 minutes.
And what about the masks? Are those like automated? Like who makes them? Does there actually
Doug
need to be a
designed
person
them.
up there?
Doug, with help from Lara, designed them. Of course, the milling process is automated, but and even the design process is automated. But there are many things you can tweak when you select. We prioritize stars according to their brightness, their color, according to where they land in, where they are in color magnitude space. If there are particular kinds of stars that are of interest, like Rohit is studying Wolf-Rayet stars, if we wanted to put, if we were observing M33, we probably would have put some of those on the mask, because we know they're interesting already, and getting another measurement, getting a time point in case these things change in brightness. These are sorts of the considerations that decide what goes on a mask.
But is it like milled and like inserted into the telescope automatically, or is there someone that
No,
like
all of
goes in between that?
It's a combination of machine and human. So when Doug finishes the design process, what we send over is a CAD file to the milling machine. But Carlos can probably say way more about this than I can in terms of how that works. But there's an operator operating that mask milling machine. Same is true for putting it into the instrument. There's a barcode that gets scanned, so it enters so the system can then address it via the barcode, and all of the changing masks within the instrument, that is all automated, of course.
Once the masks, so the slit mask exchanger, it's like a cassette, and it can load up to 11 masks. So every time that there is, like tonight, Raja is observing, but tomorrow we have a different observing team that is going to be using DEIMOS for the first half of the night. And they want to use a few different masks than the ones that Raja is using tonight. So those masks went through the same process as Raja's. They submitted, this other observing team, they submitted their design files. The masks were milled at the summit, and tomorrow during the day, after sunrise, there is going to be one of our support technicians. These are specialized technicians that they work on the summit. They will look at the list of masks that need to be installed tomorrow on this cassette in DEIMOS, and then they have a procedure to remove. There are like 3 new masks tomorrow so we'll remove 3 of the masks that Raja is using tonight will be removed, and then 3 new masks will be installed in the cassette. And that's the same for the filters and for the gratings. So they are all configurable elements. And then once they are installed in the instrument, as Raja was saying, there is this barcode system that is used to tell the software what of these configurable elements are installed in the instrument. So that it's like each mask has an identifier, and the software needs to know what that identifier is. So when Raja goes and selects a mask in the software because wants to observe that mask, that is the actual, we know that that is for sure the mask that the software is selecting, that there is not some sort of, and that's a critical step actually, because the worst thing that can happen during an observing run or during the night is that you think that you have one mask in the instrument and then you insert it and it's not the mask that you thought it was. So yeah, there is some human intervention in it, in the entire process.
Exposure
But
complete.
once that handshake between the software and the physical masks that are installed in the instrument once that is done during the day, then at night everything is automatic. You just out of the 10 masks that are available for you to select, you select the one that you want. Same with the filters, and the same with the gratings. You have 2 possible gratings. So yeah.
Wait, I thought the max was 11. Why do you have 10 available?
Sorry, 11. Well, there are
Okay.
11, but there is one mask that is used to focus the instrument internally, and that mask is always there. So that's so really like
CCD
exchangeable.
readout complete.
10.
And why do you only take out like you were saying that if the next person has like 3, you would only change 3 of them. Why not like change all of them every night?
Well, because there is no, this process of physically, this person has to go there. We have a drawer with all the masks and needs to check which masks are going to be installed today for tonight. And then needs to put the masks in a case, walk from where the masks are stored in the same building to the dome where the instrument is, and then needs to take out the masks that are not going to be used anymore and then install the new ones. All that takes a lot of time. I mean, it takes time first because you are working at 14,000 feet, so oxygen is lacking, and it's a process that takes time, and these support technicians and instrument technicians, they have many other things that they need to take care of to get the telescope and the instruments ready for the night. DEIMOS is not the only instrument that is going to be used tonight on Keck II. On the second half of the night, we have a different instrument, and then there is another telescope, which is the Keck I telescope, that is also using a different instrument. So this crew that is working on the summit during the day, they have to prepare everything, the telescope, all the instruments, to be ready for the night. So what they try to do in their daily operations is to optimize all the processes and procedures to make it safe, but also as efficient and as quick as possible, so they can get through all what they need to do during the day. So if you only need to replace 3 slit masks, it doesn't make any sense to take the other ones out. And if you take the other ones out, which ones you could insert anyway? I mean, if no one is going to use those masks, what would you put in instead of those ones?
So they can't be empty. It's just
they could be empty.
But there's nothing gained from emptying the cassette.
There is no reason why.
It's just extra work.
Fair enough.
Yeah, you just optimize the work essentially. So.
Yeah, cool. Thank you.
Welcome.
Yael, what are you guys going to look for? Observations or?
No, so I'm in Alex Filipenko's like intro to astronomy class, and he's taking a bunch of us up to for the day. Yeah. It's gonna be giving us a little tour and whatever.
I see. Oh, that's fantastic. You've been there before, right?
Yeah, I've been a couple times. Yeah.
We went last summer, right? You didn't you go last summer?
Yes,
Yeah,
I
okay.
did. And I also went in like August because there was the meteor shower. So a couple of us from Berkeley like headed up
Gotcha.
just to like have a good viewing spot.
Gotcha. Did you see the comet by any chance?
I did. We went on they would open the roof of the Astro building because we have like a really nice telescope up there.
Yeah,
So for
Campbell
about a
Hall, right?
week, yeah. Yeah, Campbell Hall. So we would use truckers and they just had it open for like a week straight just so everyone could see the comet. It was really, really nice.
Oh, that's
Like
great.
even with all the lights of Berkeley, like we could still see it well.
That's great.
Also, there is a question in the chat.
Oh,
What challenges do you face when interpreting the data from these telescope systems?
many. Well, I can describe a few, but let me see, where do I start? It's a good question. It's a good question. I see two questions on the spectrograph. I see a second question about, I thought I saw a second question, but that's gone now. Okay. So one of the things you deal with any telescope or instrument is ultimately you're reading a silicon device. You're reading information. You're reading information off a silicon device, right? So you want to be careful that what you're measuring is not an artifact of the instrument. I'll give you an example. If you look at this, I'm going to zoom in on this, or I'm going to pan around here, right? So this instrument has sharp edges, right? There's silicon devices, they have sharp edges, etc. So this gap, for example, in the spectrum between the blue and red halves that we were talking about, that gap is nothing astrophysical. That's an instrumental gap. There's a gap in between the two pieces of silicon. Interpreting, compensating for, correcting for, avoiding instrumental artifacts is an important bottleneck. That's one of the things you have to make sure you understand before you can properly interpret the data. We're interested in the astrophysics of the spectrum, not what the instrumental characteristics are. But we need to understand the instrumental characteristics so that we're not misinterpreting an instrumental signature with an astrophysical signature. Right? So that's one. For telescopes like Keck that are on the ground, the light is shining through the Earth's atmosphere. So it's we have to account for atmospheric effects and make sure, again, same thing. We don't want to misinterpret something that the Earth's atmosphere is doing with something that's happening in astrophysics. So these are important things that by way of interpretation. After you've corrected for these two things, we're trying to study Andromeda stars, but occasionally we'll run into things in the background. So in fact, what Sarthak and Abdullah are studying are background galaxies behind Triangulum. So background objects, instead of being stars in Triangulum, there are background galaxies. So identifying and removing them is important. Otherwise, if you misinterpret them, if you say, oh, we think these are stars in Triangulum or Andromeda, then you're going to mess up your conclusions. Not you, but whoever misses those. So correcting for background contamination, foreground contamination, these are all important steps towards proper interpretation of the data. But you could see that was a good question. There's a lot of subtleties to it. Another question was about on the spectrograph, what indicates intensity? Is it the thickness of the line streak? No, it's actually what you're seeing here in this image is really interpretation of, what's the word I'm looking for? Number of electrons collected by the silicon device is what's being translated to a color. So when you see an intense white, that means a lot of electrons were collected by that pixel. A lot of electrons were collected by that pixel because a lot of light landed over there. So ultimately, it's an intensity value at every pixel that's been interpreted, that's being shown as an image here. That makes sense. Yeah, I've been taking pictures of I had been taking pictures of the comet before it faded. Right. See how are we doing on that? So we're on the third exposure. Less than 10 minutes to go. Less than 10 minutes to go. 9 minutes to go. Yeah, we're almost halfway through the last exposure of this mask. Halfway point.
Were you able to see the comet well from Santa Cruz?
I didn't try from. Oh yeah, I did one night from the. We had gone to. There was a resort in near Santa Cruz that we were doing an outreach event, and we saw it from there. I saw it from home in Los Altos. Yeah, took pictures on my phone. Julie, I've highlighted the next target, but we're not ready to move yet.
Okay. This will be the last exposure on this one.
We're on the last exposure on this. I'm just going to double check with Doug that that's indeed the object that the target we want to go to next is BB.
Okay.
Oh, actually, I have it in the spreadsheet. Let me see what mask comes after RB. Oh, we're at BA now. Yeah, BB is what we want next. Yeah, I've got the correct one highlighted, Julie. All right.
Okay.
Let's see.
Thanks.
And this one will require a slight, it's not a big slew, but a slight slew.
Okay.
But
And then
if we do
looks like
one
we'll
more
do
mask after this,
yeah, it looks like that'll be RB without a slew.
that won't be a
So
exactly B. Yeah.
if I don't slew, you'll need to change the object name manually.
I'll just change the object name. We won't change anything else. Yeah.
Okay.
So we'll change the object name in, where do we do that in the, is it in the course align step?
Well, so what is gonna happen is that when you do the fine alignment, it's gonna set
Complete.
the object name to the mask name space align. So I think, yeah, you want the object name to be completely different to the, I mean, you want it to be different to the than the mask name. You want to do that after the final alignment is completed.
Got it.
Mhm.
But that won't be this next change, but it's the change after that.
Okay.
He doesn't have to change the name with the keyword or something if I don't slew.
No,
Okay.
he can do it on the GUI, Julie.
Ah,
So there
thank
is
you.
a box on the DEIMOS control GUI that is essentially the object name, which changes.
cool.
I mean, it changes the keyword.
Yeah. Right.
But
Okay.
you do it on a GUI. So.
Awesome.
Got it.
Thanks. Thanks,
Okay.
Carlos.
So I would change the mask, slit mask, and then I would, where it says object under detector control, I would change it there, right, Carlos? Is that what you?
Yes,
Okay.
that is correct. Yeah, that's correct. And then while you are doing the fine alignment,
Mhm.
the object will automatically change to the mask name space align.
There at last, Gus, are you sure?
And then, so that's why you need to verify once you are happy with the fine alignment, you're going to have to change the name again to the name that you want.
Got it.
Hello, Raja, I'm back.
Doug, we are going to go to, after this exposure is over, I've highlighted BB. I confirmed on the spreadsheet that that's the correct one.
Yeah.
We can just update the times. That's the only thing. Because one of the things is we are soon, in an hour, we are going to hit transit. So beyond that, the AMS will actually start increasing again. So the seeing might get worse. So we may, it might not be, if we can shave some more time off even in the alignment, that may not be a bad thing for the last mask.
Well, the last mask, our SRB, is again in the same position as SBB and is using the same alignment and stars.
It should go quickly.
Yeah.
Yeah. We were just talking about the process for that, and we wouldn't do a course align. We would just do a fine align. Actually, we would do a fine align even though we are going to the base position.
So we have, it looks like, yeah, a bit over 3 minutes or something.
Yeah. Not
Or
even
a bit
that.
over, yeah, 2 minutes.
100 seconds, right? Right now. Listen to. I think the bright stars, Doug, are, the blue masks are targeting fairly bright stars. This is in, there are main sequence stars and stuff like that that are quite bright. So
yeah,
they got very good signal on these.
Yeah, it's going well.
Yeah, it is. Touch wood. The Z-specking is also going well. I have finished 3 of Miranda's 4 masks from 2022B.
Okay.
The 4th one, partway done with that. I hope to finish that this
Miranda's?
weekend. Miranda's M33 masks, yeah. I mean, Margaret's, but they're for Miranda's paper.
I see.
And then you'll run the Weeksian and carbon on those.
40 seconds to go.
Okay.
Let me select the next target. Did you already select it?
I did already, yeah.
Yeah, SBB. Okay.
BB. I'm going to switch masks as soon as this thing is done. And then you work with
Yeah, I think yeah. I can do the same thing.
Same thing. Okay.
Exposure complete.
Okay, Julie, if you can hear us, I think we're good to slew to the next highlighted target.
Okay, moving now.
Thank you.
It's so confusing because there's a B at the end. Oh, sorry, there's always an A at the end. So SBB is an SBBA. It
Yeah.
always gets me. Is the mask correct in control 0?
Yeah.
And it's restoring to 0.
DCD readout complete.
It's going to 0th order there. So I'm going to go to our final alignment thing. Set up for it. Oh, yeah. So here's what you're saying. We should.
We go to course 1 and I can load the correct mask.
But we're not going to grab a guider. We're not going to move it. We're not going to move the telescope.
Well, we're going to move the telescope now. We're not going to move it from this one
you're
to the
right.
next
You're
one.
right. Absolutely. So I'm so sorry. I completely messed up. Yeah. Absolutely. You do want to grab a guider image once Julie said. Sorry, I was one mask ahead already.
Yeah. I think it's still rotating to the right, PA.
Mm-hmm.
Are we guiding?
Not yet, I think.
Oh.
Right, Julie? We're not there yet, right?
Okay. Sorry.
Hey, I had a little trouble choosing a guide star. So I'm guiding in the mask area. So if you want to take it out, change it or something, make sure to let me know first.
Yeah, we shouldn't need
Otherwise,
to.
you're good to go.
Thank you, Julie.
Good to go then.
Okay.
You're welcome.
I'm going to grab a guider image. Yeah, we have a couple of really bright stars on the mask, so it should be good.
Yeah.
Doug, go ahead.
I'm going to select this one if that's okay.
Yeah, that's clean, nice and isolated. Beautiful.
Okay. We're good to do this?
I think so, yeah. I'm just going to check something. Yeah, you're good. Yeah, it's changed the integration time to 20 seconds. It's
So you're doing directly final alignment, is that right?
yeah, because this mask involved a small slew. It's the next change that will have the. I was confused. Sorry, Carlos.
Oh, so you were one step ahead.
I was
essentially.
one mask ahead. Yeah, one entire
Okay.
mask ahead, not just a
Okay.
step. Yeah.
So Julie, you said that you didn't find anything to guide on the mirror side?
Exposure complete.
Julie? Julie is talking to someone else. Hey, Julie. So just quick question. You said that you didn't find anything to guide on the mirror side of the guider, or?
DCD
Yeah, I mean, I
readout
just didn't really like any of the stars there. They all had kind of low signal noise ratio.
I
The
see.
one that looks best is right on the edge.
Yeah, I got it. Yeah. And then the other one that is kind of to the right looks like a double star or something like that, isn't it? It's like
Yeah,
elongated.
it looks fuzzy. It looks like
Yeah.
it's not a regular star.
Yeah.
Arena's over here, and she was saying that maybe the flexure is even better if we're guiding on the mask anyway. I don't know. Is that true?
Not because when you see how it's
Not really.
internally the mask gets inserted in the optical path, and the mirror is just above the mask. So they are almost, there is no relative flexure between the mirror and the mask. There is no way you can have
same either way.
Yeah, I think it will be the same. I mean, the entire guider camera can move with respect to the two, but I don't see how you can move the mask with respect to the
DCD
mirror
readout
once the
complete.
mask is inserted.
Okay.
But yeah, that looks good. That one looks
That
good.
looks good.
So.
Yeah. Even the first one looks good, right? So I'm just going to send moves retake.
Yeah.
It looks like there's a slight, I mean, there's no rotation. I wonder if I could have just, anyway, it's quick. So
Yeah,
I'll
just for one. It's okay.
Yeah, it's not worth it.
And then okay.
And Doug, we're going with 18 minutes, right, for this one?
Yeah, I think so.
Okay. Yeah, the thing looks good still.
Then this is after this one is the last one.
After this one is the last one, yeah. This is the second last.
Exposure complete.
I think. Is the Shadow of the Scientist 2 hours, Roger?
Yeah.
DCD
just at the end of it.
complete.
There is a question for you there on the chat, Raja. I don't know if you've read it. But...
I haven't. I'm just going to finish the alignment here, but I'm going to eliminate box 1. It's a bit too close.
Which one?
Star 1. You see that
yeah,
back column?
There is that back column. Yeah, yes, maybe remove it. Yeah.
And there's a slight rotation, so I'm going to send moves and retake.
Yeah. I mean, it seems that it had.
It's close.
Calculate the centroid correctly, but since you have 2 on either side remaining, I think it's better to remove that one.
Yeah, I figured, yeah.
I don't know what happened with all your stars number 6. They were a little bit too far to the left there. Because they didn't show up in any of the.
We had a similar problem in September, and Michael was saying that there's something about the mask design software that's allowing guiders to be put too close to the edge.
Yeah, I suspect that makes sense to me because, yeah, that probably will need to be addressed on the new slit mask design software.
DCD readout complete.
Having said that, we're very excited about the new software not having to go back to IRAF.
Oh my God, yeah, it's such a.
This is
You're
done.
online.
This is done. Very good. Okay. Julie, please mark base. This is going to be an important one to mark base for because we're going to come back to exactly this position.
Okay, base is marked, and I'll write down the parameters.
So we can start the 18 minutes.
Yes, please. I'm going to start this command here. It's going back to 7200. The mask is correct, filter is correct, name is correct. I think we're good. We're now just waiting for FCS to catch up. So we can watch that.
Okay.
Let's wait for the next update. We'll figure out how far away we are from FCS for FCS.
Yeah, the gradient field is in yellow because of that. Oh, that the 100.
There we go.
Yes.
It's quite far away.
So what was the question on the chat? And then I think that could be.
Yeah, that should be the end of our session.
Yeah,
after that.
it says, can you?
Yeah.
Oh, go ahead. Sorry.
Oh, I was just gonna read off the question for her.
Yeah,
Do you wanna go ahead?
you can go ahead.
Okay,
Okay,
the question was, can you share your most significant discovery or the most fascinating discovery about stars in Andromeda?
Depends on who you ask. Or our most fascinating, significant discovery about stars in Andromeda. Doug, what is it for you?
Well, for me, I think it was probably the discovery of the GSS back in the early that was pretty exciting to see such a massive stream.
No, but it's I think the
For
question is
us,
about
for
your
us,
most significant.
Yeah, I think weak seeing stars probably,
Yeah.
and the possibilities there. But in general, for me, it's the GSS.
Okay. For me, it would have to be, the Vixian and also the discovery of the most distant stars in the Andromeda halo. That was way back when, 2005. But I think we should call the shadow session to a close. So thank you all, and Julie and Carlos and Doug, I'm going to go back to the Keck Zoom link then.
Sounds good. See you there.
Thank you, folks. Bye-bye.
Bye.
Thanks, everyone.
Bye, everyone.
Thank you.
Thank you, Julie and Carlos, for hopping onto this.